at 8:30. Let's go and get started. Good morning, everyone. How's everyone doing today? Good, good. Second week. Not too stressful yet. No midterms just yet, so hopefully everyone's doing good. All right. So the plan for today, we're going to continue our review of differential equations, and so we're going to finish up first order equations today. We just have a little bit more to tackle with that. So I have an example of integrating factor and just a little bit of conceptual information for integrating factors. So that should take maybe the first 20-30 minutes of class today. And then after that, we're going to move on to second order equations, which is where we're going to spend the bulk of kind of our time here on. Announcements. So homework one, remember homework one is out there. I know people have started working on it. So remember that is due this Thursday by 11:59 p.m. After today, you should be able to do everything on it. And so I think some people came to my office hours yesterday, and people were make sure you're working on it. If you're having trouble with it, I do have office hours tomorrow, and I have office hours Thursday. And so there you have those times to come by and ask the questions. I don't have any office hours today, but if you do want to meet today, just let me know. I can see if I can fit an appointment time. All right, and so that's the plan for today. Are there any questions I can answer before we get started? Great. Okay, all right, and so let's go ahead and pick up where we left off. And so last time we were talking about first order differential equations, in particular linear first order equations, which we normally solve with integral. All right, so let's refresh our memory about what a linear first order ODE looks like. So linear first order ODE takes the following form. So we have y prime plus x y is equal to the following. And the most important feature of this form is the fact that whenever you see a term with y, whether it be a derivative of y prime, or y by itself, it only appears in the first order. And so this concept of linearity, this concept of a linear ODE, it's going to come up again. In fact, it's going to come up later today when we do second order equations. So I really want to kind of drive that point home. Okay? And so when people say an equation is linear, what they mean is that what they specifically are referring to is the polynomial order. Okay, and so you don't have any y squared, you don't have any dy dx squared or y prime squared, or any y to any weird power, like 1/5 or something like that. Okay? And so it's purely just first polynomial order. All right. And so, compared to our separable equations, these are a little bit more challenging to solve because of the presence of the right-hand side, r of x, and because of the presence of the p of x term. We can't really solve this using separation of variables. So we need a new technique. But what we would like to do, and kind of what we find the easiest to do to solve these kinds of equations is to use direct integration. That would be kind of the easiest way, right? Because at the end of the day, we have differential equations, and the way that we undo a derivative is we take integrals. And so by using an integral, that would be kind of the best case scenario, the easiest way for us to solve these. The problem is that, because of the form of this equation right now, we can't really use direct integration because, there's kind of too many terms. So we have to kind of manipulate this a little bit. We have to get it into a better form that we can actually use direct integration. And so this is where we introduce the concept of an integrating factor. So the reason we call it an integrating factor is that it's a special function where we basically multiply this by our equation to get it into a convenient form. And so the way an integrating factor works, in essence, basically, you're going to be multiplying that integrating factor by this entire equation. And so usually we use the symbol mu. So this kind of u with kind of the little extra stuff in the beginning. This is I call it mu, okay? Or I don't call it mu. It's the Greek letter mu. So what I'm going to do is I'm going to take this equation up here, the box equation, and I'm going to multiply that entire equation by mu. Okay. Right. And so if we do that, we end up with the following. We get mu prime plus mu of x y equal to mu r. Okay. Now I was a little bit sloppy with the notation just now, but the mu is going to be a function of x. And so it's not a constant, it's actually going to be a function. And so ideally, by multiplying by this factor, by choosing this integrating factor cleverly, we can turn this equation into something that looks like. Mostly it's the left-hand side we need to work. So we're going to turn it into something that's mu multiplied by y, okay, prime. Okay, so that prime or that derivative is being applied to the entire quantity in d times y. And the right-hand side, we're just going to leave it alone. Okay, so the right-hand side is just going to be mu of. Okay. So that's ideally what we want, right? And so ideally, we're multiplying by this integrating factor, and we turn the left-hand side into, basically what this is called is a perfect differential. Okay. And because a perfect differential, you can just integrate that straight out. Okay. And so the question now becomes, how do we get here? So how do we choose mu such that we get this kind of perfect differential form? And so to kind of tell us what mu has to be, let's kind of work, we'll kind of work backwards. So this is kind of where we want to end up. Okay, this perfect differential. And so what I'm going to do is I'm going to apply the product rule on the left-hand side. You'll see me use this acronym quite a bit. So I'll use LHS. LHS stands for left-hand side. Okay. Yeah, you've never seen that before. Right, so we apply product rule on the left-hand side. What we get is derivative of the one function multiplied by the other plus derivative of the other function multiplied by. We have mu y prime plus mu prime y is equal to mu. So all I did in that step was I just applied the product. So no product rule is derivative the first time, second plus derivative the second time first. But I kind of swapped them just to make it a little bit easier. what I'm going to do is I'm going to compare these two equations because they look pretty similar, right? So they all have kind of the same number of terms. They all have a y prime term. There's just a couple kind of small differences. All right. So let's look at these terms. Okay? So both equations have a mu y prime. Okay? So those are going to be the same. So we're going to ignore those terms. On the right-hand side, we have a mu r of x. And so those terms are also exactly the same. So we're going to just ignore those. Where these equations are different is going to be in the second term. And so in the second term, for the first equation here, remember that first equation we obtained just by multiplying our original equation by mu of x. Okay? We have this coefficient mu p of x. And in our second equation here, we have mu prime. Okay? And so the reason I boxed those two terms is that in order for this integrating factor to work, this kind of gives us a relationship, or this gives us a guideline for what mu has to be in order for this integrating factor to work. Okay. And so basically what I'm going to do is I'm just going to equate the two boxed quantities. And so we're going to say that mu, and I'll go ahead and add mu of x just to kind of remind us that it's a function of x. Mu of x times p of x to mu prime. Right? So this is an equation that tells us what mu has to be in order for it to work. Of course, we get another differential equation here, and so we have to solve another differential equation. It's kind of a recursive thing. In order to solve one differential equation, you have to solve another differential equation. When I was young, there used to be a show on TV called Pin My Ride, and the host of that show was a rapper named Exhibit, and then he became kind of famous for doing all these ridiculous things and putting inside cars. We heard you like this, so we put this inside your car. So it's kind of the same thing. We heard you like differential equations, so we heard a differential equation inside your differential equation. In case you were sick of that already. Okay. The good thing about this equation right here is that we can use our old technique, the separable equations, to actually solve this. Okay. So I'm not going to go through all the details just because we've done that many times before. But what you end up with is that our function mu is going to be an exponential function. It's going to be e to the integral e of x. And I believe that was kind of the last thing that we talked about at the end of class last time. This equation can be integrated. Okay? But this is where it comes from. So it doesn't just come out of thin air. It comes from this kind of motivation of, first of all, we want to get a perfect differential. And in order for that to happen, you have to have this. All right. Any questions on this so far? Okay. All right. So let's go ahead and plug it in. Right? And so let's go ahead and solve our equation now. And so now that mu has this and solve our original equation. All right, so original equation, I'm gonna go ahead and start it from its perfect differential form. So we're gonna have u of x times y of x prime. Remember that prime is nothing more than just a derivative with respect to x. Okay, this is equal to mu of x r. Okay. So now that we assume that u takes that form, we can kind of jump straight ahead to this form of the equation. Let's go ahead and integrate. And so we integrate this equation. We're going to integrate the left-hand side. We're going to integrate the right-hand side. Okay. And so here's where our perfect differential form comes in handy, because now this perfect differential and this integral, these are kind of reciprocal operations. So they're just simply going to cancel out. And so on the left-hand side, all we're left with is mu of x, y of x. And on the right-hand side, we can't really simplify this any further right now because, we haven't specified what r of x is. We haven't even specified what p of x is. And so I'm just going to leave that in integral form. But I am going to add my arbitrary constant. Remember, whenever we do an indefinite integral, we have to add our arbitrary constant. Next, I'm going to do is I'm going to simplify. I'm going to solve for y of x. Okay. To solve for y of x, I'm just going to divide by mu of x. Okay, so we have 1 over mu of x and integral mu of x plus 1 over mu of x times c. Okay. I'm going to do one more step here, just so I can highlight kind of something, a certain feature of the kinds of solutions you usually get here. So I'm going to plug in for mu of x. Remember, our expression for mu of x is e to the integral p of x dx. Okay. And so when we take the fraction of that, then one way we can do that is just turn the exponent into a negative. And so we have y of x is equal to, we have 1 over mu of x. 1 over mu of x is just going to be e to the minus integral mu of x. Integral mu of x. Integral e to the integral p of x dx. Plus e to the minus integral p of x dx times. So this right here, this would be the general solution of a first order linear differential equation using integrating. Okay. Normally, I don't like to show this because, in my opinion, when you're solving differential equations, it's not just kind of plugging into a final result like this. It's more about the process. Okay? And so going through the process, just like we did last time, I think is more important than just plugging into the final. Normally, I don't like this because I think kind of what this encourages is that if you do have a linear first order ODE, technically you can just kind of plug into this equation here and get the solution. Okay? But the reason I do this here is so that I want to highlight some things about the solution that you're going to see quite often in a lot of physical problems that we're doing. All right. So before I do that, though, are there any questions on kind of the process that we took to get here? Okay. So let's look at this solution. Right? And so, I do have one example planned out for this, but I think if we go over this form here, it's going to help make a bit more sense. All right. And so if you notice from this solution here, we have two terms. So they're separated by a plus sign. And so we have one term here on the left, kind of the big term. And then we have another term here on the right. And that term on the right involves our arbitrary constant. Right. And so when you have differential equations that model that model physical behavior, oftentimes these terms come from specific things within the physical system. And that'll make more sense kind of as we do more plots. But let's go ahead and label some of these. So let's start with the right axis. So the right is a little bit simpler. And so the right term, this is the term that involves our arbitrary constant. If you remember from last Wednesday, or last Thursday, the way that we solve for this constant is by applying initial conditions. And this is not going to be any different. And so oftentimes I like to call this term the initial condition term. Because its behavior is governed very largely by the initial conditions. Okay? And so what you apply for that constant C is going to determine what this term does. Okay? And if you'll notice, the term that's multiplied by the C is a decaying exponential, right? So e to the minus something. Okay? And if you kind of recall kind of what a decaying exponential looks like, it decays over time. Okay? And so for most physical systems, when P is a positive number, and in most cases it is, what you'll see is that this term, as time goes on, or as x gets to a large number, it tends to just kind of go away. It kind of just tends to decay down to zero. And so this term is often called the transient term. And the reason for that is, just like I mentioned, when you get to large values of t, or large values of the independent parameter, large values of t, large values of x, this term here kind of just goes away. Generally. And so that makes sense, right? And so when you have a term here that's governed by an initial condition, okay, by definition, an initial condition only happens at the very beginning of your equation. Okay. As you start to get further and further away from that initial condition, or further and further away from the boundary condition, then that really doesn't seem to matter all. Let's look at the other term. So the other term, the key characteristic here is actually R of x. And so when you're looking at physical systems that are modeled with a differential equation, R of x often takes the form of some kind of external force. And generally speaking, that external forcing is going to persist for a long period of time. So, for example, the problem, I think problem 3 on the homework, and it's very similar to the example that we're doing. That forcing term is given by a battery in an electric circuit. Okay? And so as long as that circuit remains plugged in, that battery is going to provide power. It's going to provide electrical current for that circuit. And so the behavior of this term is actually the opposite of the previous term. Okay? And so, instead of kind of going away with time, this is something that persists. It only persists at large values of time. And so because of that, we often call this the steady state. I've circled kind of the most important takeaway. So whenever you solve a linear first order ODE, generally you get a transient term, which is something that goes away with large values of time, and you get a steady state term that kind of persists at it. And so I'm mentioning this here. I mean, obviously we're going to see it in the next example, but this kind of behavior is something you'll see in second order ODEs. Okay, so this concept of like transient and steady state, initial conditions versus forcing, this is going to come back, very soon as well. Okay, so it's kind of important to kind of get that. And I know that just talking about it generally kind of makes it, it's hard to kind of visualize it, but kind of as we do more and more examples, like the one we're about to do, it'll start to make a bit more sense. Okay, but I really want you guys to think about transient versus steady state, and kind of connecting that with kind of the physical properties of the systems that we're going to. Right. Any questions on this before we jump into an example? All right, so this example is very similar to problem 3 on the homework. Okay, so if you're working on that, then this would be good help. It's a little bit easy. I will say it's a little bit easier than the homework problem, but a lot of the same concepts still. Okay, so for this example, we're going to look at an electrical circuit. In particular, we're going to look at what's called an RL circuit, which is a circuit with a resistor and an inductor, and we're going to include a battery as well. Visually, it looks like this. So first we have the battery, then we have the resistor, and the inductor will put the circuit's connected on this terrible way. My wife is the artistic one. Funny moment happened yesterday in one of my lectures. Like I kind of poked fun at my wife, and then I kind of made a joke about her, and then right afterwards I started coughing because I swallowed some spit down the wrong hole. So I'm going to make it a point nowadays to compliment my wife at least once a day, just to make sure that bad things don't happen. Okay, and so if you apply Kirchhoff's laws, and we're not going to do that in this class, it's not a circuit class, so we're just going to jump right to the equation. And so the ODE that governs the circuit looks like the following. So we have di dt, and so that's the time derivative of the current. Okay, so big I here represents the current in the circuit, plus R over L times I is equal to E of t, which is the battery, divided by L. And for this example, we're going to assume a DC circuit, and so the battery is going to provide a constant amount of voltage. So E of t, where you big E is going to represent the voltage in the battery. All right. And so now that we're given this differential equation here, we want to solve for the solution I of t. Okay. All right, so here's our setup. And so we have a circuit, we have a differential equation, and we're looking to solve for it. All right, and so first of all, the first thing that we notice here is that we have a linear, non-homogeneous first order differential equation. Okay. We know it's linear because our dependent variable I never appears with a power that's not one. So dIdt is raised to the first power, and then we have I in the second term, also raised to the first power. Okay, so we have a linear. And so because it's linear, we're going to be able to use integrating factor to solve this. Right. We also know this equation is not separate. And so we're not going to be able to solve this with separation of variables. So our only option here is to use integrating. Because if you try to separate out the variables, and so let's say that you divide by I, okay, so you move the R over L I term to the other side, you divide by I. There's no way to kind of eliminate it from those other two terms at the same time. So we have to solve this equation. All right, so let's go ahead and start it. And so for integrating factor, we need to identify what our P of X is. Okay? In other words, what the coefficient in front of our I term is. So the coefficient in front of our I term is R over L. Okay, so this is our P of X. I put it in quotes here because our independent variable here is T and not X. And so technically it's a P of T. Or I guess even more technically, it's just a P, which is a constant. And that means our integrating factor is E to the integral. E, in this case, P of T dt. Let's go ahead and plug in our value of P. It's E to the integral, R over L dt. Okay. The resistance and inductance are both constants, as they usually are in circuits like this. And so we just pull those out of the integral, we integrate dt. So our integrating factor here is E to the R over L t. Okay. Going on Zoom questions. All right. All right. So now that we have mu, we're ready to plug this in, and so we're going to plug this in for a perfect differential form. Okay? Remember, what we just finished talking about was that if our integrating factor has this form right here, and we kind of multiply this by a differential equation and we kind of plug it in, we end up with an equation that looks like the following. So we have 2 times t multiplied by I t prime. Remember, that was the whole point of the integrating factor, so that we get a perfect differential on that side. This is equal to mu of t r of all right, so let's plug in for mu. So mu of t we know is e to the r over L by t e prime. This is equal to mu, which is e to the r over lt times r of t. And so in this case, our r of t is also a constant, and so it's just going to be e over L. So now that we're at this point here, we can simply just integrate it because we have the perfect differential. This. Once again, we have a situation where we have the integral and the perfect differential on the left-hand side. Those are going to cancel out. And so on the left, all that we're left with is over L times T times I T. And on the right-hand side, we can go ahead and perform that integral. And so E over L is just a constant, and so we can just pull that out of the integral. One of the nice things about integrating constants. Okay. And then all we're left with is the integral of E to the R over LT. And so let's look at the inverse chain rule. We do inverse chain rule, we take kind of the coefficient in front of T and E to the R over LT, and so that's L over R. Okay. And then the integral of E to the T is just E to the T, and so we just kind of pop that guy just right up. And we can't forget our arbitrary constants. All right, so let's take this equation, let's simplify it. Let's solve for I of t. Okay. And so to do that, we're going to divide both sides by e to the r over lt. Okay, so if we divide both sides by e to the r over lt, this and this, we're going to cancel out. Okay. Right, and so that first term, and of course these L's are going to cancel out too. That first term is just going to be E over R. And then for that second term, we have C divided by E to the R over LT. Because we're dividing it by a function of T, we can't just lump it into the constant. I know I did that a lot last time, but you can only do that when you're multiplying C by another constant. In this case, we're not multiplying by a constant because it's, we have this function T. And we have E to the minus LT. And so this right here is our general solution. Any questions on how we obtain this solution? Okay. All right, and so that's the process of integrating factors. Okay. So not too bad, you know. Usually for these types of equations, you just identify what the key term is, you plug that into your expression for the integrating factor, and then you just kind of just plug and chug it over. All right, but we're not done yet, and so because this is a physical problem, let's go ahead and apply an initial condition. So, I kind of forgot to mention the initial condition before we started. So the initial condition is something that's going to be given to you in the problem. It's not something you make up. Okay. And so, normally this initial condition is given at the beginning, but just kind of forgot to mention it. Okay. And so for this particular problem, we're going to assume that our circuit starts from rest. And so the initial condition is that I of 0 is equal to So let's go ahead and apply this initial condition and solve for C. Okay, so let's take our equation up there, and everywhere that we see t, we're just going to plug in 0 for t. And then because of the initial condition, this is all going to equal to 0. Let's go ahead and simplify this. And so we have E over R. E over R is just chilling, with we don't have to worry about that. Then we have e to the minus r over L times 0. So that's going to be, we simplify that, that's going to be e to the 0. We know e to the 0 is just 1. Right. And so if we simplify this, we have e over r plus c is equal to 0. Okay. And so at this point, we have this simple algebraic equation, and so we can just solve it for c. And so we get that c is equal to minus e over r. All right, let's go ahead and plug it in and then get our final solution. Our final solution I have p 2 e over r minus e over r e to the minus. Just to simplify this a little bit, you don't have to do this, but I like to do this just to make it a little bit simpler to write. I'm going to factor out that e over r. E over r times 1 minus e. That's our final solution, particular solution. Any questions on this? Okay. So normally, this is kind of where you would stop, for an equation. We satisfy the problem, we solve for the solution. But let's look at this just a little bit more, just so that you can kind of connect this to this idea of steady state. Let's look at our solution. And I think actually this side is actually going to be a little easier to see. All right, so our first term, e over r, right? It's a constant term. And so if you kind of backtrack, and so if you kind of look at our solution process that we followed up at this point, that e over r came from the forcing term, came essentially from the back. So this is going to be our steady state term. Whereas that other term, the minus e over r e to the minus r over lt, we essentially solve for this from the initial condition. Right? So you can kind of backtrack through our solution method, through our example, to find that that's true. So this is called the EGME. Remember, you don't actually have to backtrack through your entire solution to figure out, which is the steady state and transient. Let's look and see what happens when t gets large. And so if you really wanted to be kind of strict about this, you can take the limit of this function as t goes to infinity. Okay. All right, let's actually look at the transient term first. Okay, so actually that's the only one with t in its solution. And so we have a decaying exponential, so e to the minus r over L of t. And so as t gets large, right? So as t goes to infinity, what do we know about decaying exponentials? Decaying exponentials go down to 0. Okay? And so as t gets large, this term just goes away. Let's look at the other term. So the other term is just u over r, just a constant. And so when t gets large, u over r is just doing the same thing. It doesn't depend on t. Okay, so even at very large times, okay, so even when time goes to infinity, that battery is still going to provide the same solution. So even though when t gets large, the steady state term is still going to persist. And you can see this behavior if you actually plot it. And so if you're ever kind of unsure about which term is transient or not, you can just plot it. So you can use Excel, you can use MATLAB, whatever you kind of feel most comfortable with, plot the solution, use your calculator. Okay. And so we're going to have t on the x-axis, and we're going to have I of t on the vertical axis. Okay. And so if you plot this, it would look something like for this asymptote, basically this where it kind of plateaus out, the value of this is e over. Where now you can kind of visually see what it means to be transient and what it means to be steady state. Look at kind of this initial part of the solution here. This is the transient. Basically, this is the part of the solution where the transient part is going to dominate. And then eventually we reach a point where we're steady state. Okay. Right, so the interpretation of the transient part kind of changes depending on kind of what physical system that you're looking at. But for this circuit, the way that we can kind of interpret the transient part is that the circuit is kind of ramping up to the steady state of current. Remember our initial conditions. So our initial conditions stated that our circuit was starting at rest. Okay, so there's no current, there's no charge in the circuit at all. And so as soon as you kind of plug the battery in, then it kind of takes a little bit of time for that circuit or that current to kind of ramp up. So that's what the transient part represents. All right, any questions on this? Okay. All right, so that's first order differential equations. And so, remember we went over two methods for this. So we had separation of variables and we had integrating factors. Okay? And we picked up some other information along the way. So we learned about kind of this idea of, transient solution and steady state solution. Okay? So I don't want you to forget that because a lot of that information is going to carry over. But now when we talk about second order equation. Okay, so let's start talking about second order. All right, so we're moving up in the world. And so, a second order ODE, basically what that means that the highest order of the derivative in the equation is now 2 instead of 1. Okay. All right, so we're going to have second order derivatives in our equations now. Because second order equations can be a lot more complicated, we're going to restrict it a little bit. Okay. And so when we talk about first order equations, we dealt with actually nonlinear cases with the separation of variables. But for second order differential equations, we're only really going to be dealing with linear situations. Remember what linear means. Linear means that whenever you see a y term, whenever you see the dependent variable, its polynomial order is just going to be 1. All right, and so with that in mind, let's write out kind of our general form for our second order differential equation. All right, so we have y double prime plus u of x, y prime plus u of x, y plus u equal to so a few things. And so, of course, all our coefficients here are only functions of x or their constants. Okay, so that's why we have p of x, q of x, and r of x. Okay, none of those are functions of y. And another thing that's important here is that this is in what we call standard form. And so what standard form, all that means is that the coefficient in front of the highest order derivative, which in this case is y double prime, that coefficient is 1. And actually, if you recall from an integrating factor, all those integrating factor problems were in standard form. Usually, it's kind of a good habit to put your equations in standard form. It just kind of makes things a bit easier. And so if you have an equation where the highest order derivative has a different coefficient, usually it's a good idea to just divide by that full coefficient to get it. All right. a couple more definitions. And so, we're going to make the different, kind of the distinction here between homogeneous and non-homogeneous equations. I think I mentioned it maybe just briefly in our first order section, but here it's actually going to make a difference in terms of how we actually solve our solutions. All right, so when I say a differential equation is homogeneous, what that means is that the right-hand side, or the forcing term, is equal to 0. And so here our right-hand side forcing term is R of x. And so a homogeneous equation is one where R of x is equal. And so basically a homogeneous equation, every single term has y, or have the dependent variable in it somewhere. So the opposite of homogeneous is non-homogeneous. And so non-homogeneous basically means that there is some kind of right-hand side forcing. And so when R of x is not equal to 0, that's a non. All right. And so initially, when we first start our review of the second order differential equation, we're going to restrict our attention to just homogeneous equations. And so we will deal with non-homogeneous later, because that non-homogeneous equations kind of needs its own collection of methods to solve. So that's kind of its own. We probably won't get to that until either late on Thursday or next. So let's start with homogeneous equations. So we're going to find our solution to the homogeneous part of the second order differential equation. All right, so one big difference that you'll see for second order equations versus first order is that because of the second order derivative, we're actually going to get multiple solutions to the equation. So it's not just going to be one, and so we're going to have multiple. And because this is a second order differential equation, we're going to get two solutions. And so when we go through our methods to solve the homogeneous part, we're going to get one solution, we're going to call it y1, and then another solution called y2. And so both of these solutions are going to satisfy the original homogeneous equation. So if we plug it in, remember we talked about last Thursday that in order to check a solution to a differential equation, you can just simply plug it back in. Okay. And so when we plug in y1, both y1 and y2, they're going to satisfy the original homogeneous equation. And so we look at our kind of a standard form here. Okay, remember our standard form is y double prime plus q of x y prime plus q of x y. And since we're doing the homogeneous part, that's going to be equal to 0. Okay. If we plug in y1 into this equation, this you're going to get exactly 0. So double prime, y1 double prime, y1 prime, and y1. Okay. And same thing if you plug in y2. So we plug in y2, you get y2 double prime plus e of x, y2 prime plus q of x, y2. You plug that in and you'll get 0. So by definition, that's what a solution to the differential equation is. So y1, y2 are both solutions, and our methods, the methods that we're going to learn are going to give us kind of 2 solutions. But most of the time, we don't want to, we like to kind of combine these into one. And most of the time it's for, purely for convenience sake. But, it also makes things like when you apply your initial conditions, when you apply boundary conditions, it's easier just to apply to just one solution. And so when I say combine, I really mean combine. So we're not just going to take one or the other, we're going to take both at the same time. Okay. And the way we do that is we use a mathematical technique called linear combination. And to take a linear combination, we take both our solutions, y1, y2. We're going to add these together. But we're going to modify them a bit, okay? And so what we can say is that when you take a linear combination, you can take each of the individual functions and multiply them by an arbitrary constant. C1, C2, C1, C2, these are arbitrary constants. Y1, Y2, these are our 2 solutions. And all this is going to be equal to y of x, which is like our master solution. And so the one solution that we primarily work with, that we apply initial conditions to, that we actually report usually as the final solution, is going to be a linear combination of these. Any questions on this so far? All right, so you may be asking, so we know y1 is a solution, y2 is a solution. So when we take a linear combination of these two, is this linear combination, is that still a solution? Because it seems like we're making a lot of changes, right? So we're multiplying by an arbitrary constant, we're adding these two together. Is this still going to work? And so we want to know, by taking linear combination, are we still getting a solution to the original equation? So, spoiler, of course the answer is yes, otherwise we wouldn't be doing this, right? Wouldn't that be wild, go through all this work and say, this is useless, we're not going to use this at all. But it is a solution. Okay? And what you can do to prove it is you can just plug it in. All right, so the details of that proof is in the notes. It's kind of more boring and tedious than it is exciting, but kind of the conclusion of that proof is yes, it is still a solution. Okay. And so when we solve a second order differential equation, we're going to get multiple solutions, and when we take their linear combination, that's how we get our final. Of course, there's some restrictions on this, okay? And so y1 and y2 have to be of a certain form in order for this to work. This only works if y1 and y2 are defined in a way such that they are called linearly independent. Okay. So that might be a term that you probably maybe heard in Math 252. Okay. But linearly independent, that's kind of just a fancy way of saying that y1 and y2 are not proportional to each other. And so what proportional means is that, proportional, all it means that you can take a constant, you multiply it by the other one, and you get the first. And so if y1 and y2 are proportional, then you would have this relationship. Okay? And so if y1 and y2 were proportional, it would be possible to select a constant a such that this were true. All values of it. And so in order for them to be linearly independent, this has to not be true. So for example, so let's say that we had y1 equal to 4x, and y2 is equal to 1,337. These two functions, y1 and y2, are not linearly independent. Because we can say y1 is 4x. Right? And y2 is 1,337x. These two functions are actually proportional to each other, even though 4 and 1,337 are pretty far apart. If we set this constant a, if we define a constant a as equal to 4 over 1,337, then this would be, it would satisfy this equation. What if we kind of make just one simple change? If I change the power of x, okay, so let's say that y2 is 1,337 x squared. Now these two functions are linearly independent. Because the powers of x are different, there's no way that you can multiply one function by a constant and obtain the other. Right, so linearly independence, or linear independence, I should say, is, it sounds very mathy, it sounds very kind of dense, but that's all it means. So, when you're looking at two functions and you're checking to see if they're linearly independent, basically you're just checking the power of x. Okay? So if they're the same, most times they're not going to be linearly independent, but if they're different, then they are going to be linear. Okay? And there's some other examples that you'll see quite a lot. Or examples that you'll see kind of in our class. Okay, if you have two exponential functions and they have two different powers of the exponent, then those are also linearly independent. Okay, so that y1 is equal to e to the t, let's say, and y2 is equal to e to the 2t. But because the difference here is in the exponent of the e term, then those terms are going to be linearly independent. Okay? So that's probably one of the most common cases you see. Another one you'll see quite a lot in this course is sinusoidal function. Okay? And so sine and cosine, by definition, are linearly independent from each other. There's no way you can multiply a sine by some numbers, by some constant, and obtain a cosine. And a twist on this is actually, if you change the argument of the sine, that's also still linearly independent. Y1 is equal to sine of 2 pi t, and y2 is equal to sine of 3 pi. These are also linearly independent from each other, but the argument inside the sine is. All right. Any questions on linear independence? Okay. All right, so we're just about out of time, but I do want to go over just one more definition, just really, really quickly, and that is initial value. And so I mentioned this because, in your later classes, they may use this terminology. Okay? And so initial value problem is actually a combination of two things. So on the one hand, you have a differential equation, and then you have the initial conditions that give you the full scheme. Right. So you'll hear this terminology. I may use it at some points in the class just because it's kind of ingrained into my fabric of my theme. But that's all I mean. So when I say initial value problems, all I mean is just a differential equation and its corresponding initial conditions. All right, any final questions before we wrap it up for today? All right, so that's all we got time for today. And so on Thursday, we'll pick this up again. We'll talk about the 3 different one solution method, 3 different techniques. And then we'll do a bunch of examples. All right, so thank you guys for coming today. I know this class is early, so I appreciate you guys coming out. Hope you guys have a good rest of your day, and I will see you on Thursday. Yes, we don't say this were just divide all of it by yes, there's one more to do on Thursday. You'd have gotten in the class. What is the request on Friday, and then are the process? Are you complete? Do you have access to the device? Okay, send me. Okay, yeah, send me an email, and then I'll put you on the Canvas site so you can get access. The school might just process. I saw on Friday there was 4 people. That's why when I asked them. I still need process. So send me an email just so you can access. And okay, yeah, both. Yeah, send me an email. Make sure you both on. Yeah. Yeah, what's up? Oh yeah, there's a type. There's a 2. I closed it up. Let me send it. I'll send an email. There should be. Okay. Yeah. Thanks for catching that. Crystal, any final questions before we wrap it up? Okay. All right. So I'm gonna close the Zoom. So I'll see you. The machine.